Good morning. So in this class we are going to see about the conductivity of extrinsic semiconductor, law of mass action, diffusion current density and Einstein's relation. So first we see what is the meaning for the conductivity of the extrinsic semiconductor. You know that there are two types of extrinsic semiconductor when we add the impurity atom with the semiconductor. So when we add pentavalent impurity, you will be having N type, and when we add trivalent impurity with the intrinsic, we will be having P type extrinsic semiconductor. So now here we are going to see about the conductivity of N type and P type semiconductor. So in N type, you know that since we have added the pentavalent impurity, the electrons are the majority carriers and holes are the minority carriers. Let me define the concentration of electron as Nn and concentration of hole as Pn in N-type semiconductor. Here in this notation, the number N and P, this number and the N and P represent the type of the charge carrier, whereas this suffix N represent the type of the semiconductor, right? Type of the semiconductor. Since it is a N-type semiconductor, we can use the notation Nn, and Nd is the concentration of donor impurity. From the basic equation, you know that the relation, that is sigma n is equal to, since it is the N-type semiconductor, we have represented the suffix is n and sigma is the conductivity. Sigma n is equal to Nn mu n plus Pn mu p into Q, where Nn is the concentration of electrons in N-type and Pn is the concentration of holes in N-type, and mu n and mu p are the mobility of electron and pi's respectively, and Q is the charge of the electron. But in N-type semiconductor, you know that if Pn, that is the number of holes, is lesser than the number of electrons, that is electron is the majority carriers and holes is the minority carrier. So we can neglect this the Pn here in this equation. So when we neglect this term, you will be carrying only the first term, which is equal to Nn mu n into Q, right? Then we know that we have added the donor atom for the intrinsic semiconductor in order to get the N-type semiconductor. So the concentration of donor atom, which is represented by Nd, can be approximately equal to the number of electrons, right? How about what about the number of donor atom we have added, that is represented by Nd, which will give the concentration of electron Nn. So the Nn can also be equal to Nd. So if you replace this Nn by Nd in this equation, you will be getting the new equation for conductivity of N-type semiconductor. Sigma n is equal to Nd mu n into Q. Similarly, if we want to derive the conductivity of P-type semiconductor, as we know P-type, it is derived from adding the trivalent impurity with the intrinsic semiconductor. So since we have used the trivalent, the holes are majority carriers and the electrons are minority carriers. The same definition we are going to use here. Instead of having N as a suffix, we have the P as a suffix here, since we have defined for P-type semiconductor. So Np is the number of electrons in P-type and Pp is the number of holes in the P-type. So Pp is greater than Np. We know that since it is a P-type semiconductor. So we have taken the general equation as similar to that of the concentration of N-type derivation. So we have taken the similar this general derivation, general expression for the conductivity, and in that if we substitute Np is very lesser than the Pp, since it is a P-type, the number of electrons, that is a minority carrier, is lesser than the number of holes, that is a majority carriers. So if we cancel these terms, the remaining will be here. So the new equation for the conductivity is sigma p is equal to Pp mu p into Q. And here it's again, here the N-p type impurity, P-type semiconductor has been derived by adding the acceptor impurity. So the amount of acceptor impurity will decide the concentration of the holes. So we can substitute this Pp, that is the concentration of holes in P-type, by Na, that is the concentration of the acceptor, number of acceptor atoms. So if you replace this Pp here by Nd, you will be getting the new equation or new expression for the conductivity of P-type, that is equal to sigma p is equal to Na mu p into Q. Next, so now we are going to see about the law of mass action. So that is the definition which is given by the concentration of the product of concentration of electron and holes is always constant at a fixed temperature, which is defined the expression that is equal to Np is equal to Ni square, where N is the number of concentration of electron and P is the concentration of hole, and Ni is defined as the intrinsic semiconductor semiconductor concentration, and this law can be applied both for intrinsic as well as extrinsic semiconductor. If it is for extrinsic semiconductor, for n-type material means you have to substitute n is equal to nn and p is equal to pn. If it is for extrinsic semiconductor, so this is for intrinsic semiconductor, that's why we have in use the suffix notation. Whereas for extrinsic semiconductor, we have to represent the concentration of electron by n and concentration of the whole by Pn. So the new expression for the law of Maxwell for extrinsic semiconductor, that is equal to Nn Pp is equal to Ni square. So for a p-type material, here for p-type material n is equal to Np. Right, p-type material n is equal to Np. So this is for n-type material, that's why we have put suffix as n. Whereas for p-type, here Np and Pp. So the Np is the number of electrons, concentration of electrons in p-type, and Pp is the concentration of holes in p-type. So this law is irrespective of the doping. Right, this law is irrespective of the doping, and depending upon the temperature. That's why we have added fixed temperature in the definition, and this law can also be used for both the majority and minority carrier concentration found in extrinsic semiconductor. Next we are going to see about the carrier concentration in extrinsic semiconductor. So we know two types of semiconductor. One is the n-type semiconductor, right? The first one is n-type semiconductor. So according to the n-type semiconductor, we know that the concentration of the majority carrier, that is electron, it is depending upon the concentration of donor atoms. So Nn is equal to Nd here. So according to law of mass action, Nn is equal to Pn into Ni square. This is for n-type. And if you replace Nn is equal to Nn is equal to Nd here, right? If you replace this Nn by Nd here according to this equation, so the new equation will like Nd into Pn is equal to Ni square. So from that, if you substitute, if you derive the minority carrier concentration, that is Pn in n-type, that is equal to Ni squared by Nt. So by knowing the value of Ni and Nt, that is the intrinsic concentration and the donor atom concentration, we can able to find the concentration of the minority carriers. Similarly for p-type, you know that for p-type, the number of the acceptor atom, that is the concentration of acceptor atoms, define the concentration of the majority carriers in p-type. So Pp is equal to Na. So again we have taken the mass action law, that is equal to Np-Pp, that is equal to Ni square for p-type. In this, if you replace this Pp by this equation, you will be deriving this one, that is Np into Na is equal to Ni square. From that, you can able to derive the concentration of the minority carriers, that is electron in p-type, that is defined by Np, which is equal to Ni squared by Na. Again, by knowing the intrinsic concentration Na and the donor acceptor atoms concentration, you can able to find the concentration of minority carriers in the p-type. Next, we are going to see about the diffusion current density. So what is the meaning for diffusion? Diffusion, it is the meaning of whenever we have the concentration gradient, there is a tendency of majority carriers to flow from one part to another part, which will give the diffusion current. So the diffusion is observed normally due to the non-uniform doping. So if you consider the p-type semiconductor bar, so this is the p-type semiconductor bar, which is taken in the x direction. So this is the point where we have x is equal to 0, right? So at 0, x is equal to 0, that is at the initial position, p is equal to p of 0, which is equal to maximum, where p is the concentration of holes, but it is not constant, but it is changing one with respect to the x due to the non-uniform doping. So initially at x is equal to 0, there is a huge concentration of the atom. Then later, when it moves in the x direction, the concentration try to degrade, that is try to decrease. That is the meaning. That's the meaning for but changing with respect to x due to non-uniform. As x increases, the concentration of hole decreases, right? As we seen in the flow. So there is a slope we have to find, which is the ratio of change in the concentration to the change in the distance. Since we have taken the variation of concentration with respect to x, so change in concentration with respect to the change in the distance, that is gives the slope that is equal to dp by dx. So dp is a change in the concentration and dx is a change in the distance. So due to such concentration gradient, you will be having the flow of charge carrier for a high concentration area to the lower concentration area, which is defined as the diffusion current. So for p type, if you want to calculate the diffusion current density, that is represented by Jp, which is equal to directly proportional to the slope, that is dp by dx. So if you want to cancel this proportionality constant, we have to substitute this constant q into dp. dp is the diffusion constant for holes in meter square per second, right? But here this slope is a negative, right? The slope is negative. So the drift current density for hole is negative. Drift current density for hole is negative, right? So to get the positive sign, a negative sign used for GP. So you know the conventional current direction, that is from positive to negative. But here in drift current we have the negative. So in order to have the positive, we have to use a negative here. So the JP, that is the diffusion current density for the holes, is minus q dp by dx. So similarly, if you want derive the diffusion current density for electron, that is equal to Jn, that is equal to plus q dn by dx, where dn is the diffusion constant of electron, whereas dp is the diffusion constant of hole. So if you add these two, right, we know already the drift current density, right? So now we have derived the diffusion current, and if you add the drift current and diffusion current, for electrons you will be having this equation, and for hole you will be having this equation. So Jn is the current density with respect to electron, and Jp is the current density with respect to holes. And here in Jn, that is current density of electron, you will be having, this is a part for drift current and this is a part for diffusion current. Similarly, this is a part for drift current with respect to hole, and this is a part for diffusion current with respect to hole. And if you want to find the total current density, you have to add the current density due to the electron Jn as well as electron Jp. So the final total current density J is equal to Jn plus Jp. Plus Jp. And the last topic is Einstein relation, right? So this is another relation which gives the relationship between the mobility and the diffusion constant, right? So the relation between mobility and the diffusion constant is called as Einstein relation. So it states that at a fixed temperature, already we have seen the mass action law, it is also defined at a fixed temperature. That means Np is equal to Ni squared, where N is a concentration of electron and P is the concentration of hole, that is equal to Ni squared, that is the intrinsic concentration, right? So here another definition that is given by Einstein relation: at a fixed temperature, the ratio of diffusion constant D and the mobility constant mu is constant. So dP by mu P, that is with respect to the hole, and dN by mu n with respect to electron, that is equal to the constant, that is kT, right, at room temperature. So at fixed temperature. So at fixed temperature, the ratio of diffusion constant D to the mobility mu is constant, right? So where K, we know that Boltzmann constant, which is given by the value 8.62 in 10 power minus 5. The product we have taken KT, no, that KT it is called as voltage equivalent temperature, which is defined by V suffix T, right? So therefore Vt is equal to KT. But you know the value of T for room temperature, T is equal to 27 degree Celsius, right? So that is equal to 300 Kelvin. How it is? So 1 degree Celsius equal to 273 Kelvin. So 273 plus 27, which will give 300 Kelvin. And hence, so this Vt is equal to 26 millivolt, right? So therefore, the Einstein relation can be rewritten as dP by mu P, that is equal to dN by mu n is equal to 26 millivolt, that is 26 into 10 power minus 3. So from this Einstein relation, we can able to derive the mobility of electron and mobility of hole. So mobility of electron is equal to 39 times of the diffusion constant of electron. So if you take this dp is equal to, if you do the simplification, dp is equal to, so from this equation, if you want to try find mu n is equal to dn divided by 26 into 10 power minus 3, which will give 39, right? So the mobility of electron mu n is equal to 39 times of the diffusion constant of electron. Similarly, the mobility of hole mu p is equal to 39 times of the diffusion constant of the hole dp. Thank you.